students, good morning. Today we are going to start our lecture number 2 of module 4. Okay. Up to the yesterday's lecture we studied or we start at the last lecture module 4, and in that lecture we completed the point McLeod gauge. Okay. Now in today's lecture we are going to study Pirani gauge. In today's lecture, we are going to study Pirani gauge. Okay. Now, as we studied in the last lecture, McLeod gauge measure the pressure or measure the low pressure or low vacuum pressure up to the range 10 to the power minus 6 torr. Okay. And similarly, Pirani gauge is also used for measure the low vacuum pressure and up to the range 10 to the power minus 5 torr. Okay. Now, see here, Pirani gauge is also called as thermal conductivity gauge. Thermal conductivity. Okay. See here, Pirani gauge is also called as a thermal conductivity gauge. Now see here, what is thermal? Thermal is nothing but the heat. Okay. And what is conductivity? Conductivity is nothing but the what amount or how much amount heat is conducted by that object or by that substance. See here, first one, we are going to study this thermal conductivity. Okay, what is thermal conductivity? See here, let's consider this is object A. Okay, and we are passing the amount of heat Q to this object, and this object A observe this object A absorb Q1 amount of heat. Okay, now second object is object B, and here also we are giving the Q amount of heat, but this object B absorb Q2 amount of heat. Now if I say Q1 is greater than Q2, okay, then I can easily say that object A have high thermal conductivity as compared to object B. Means this object A absorb maximum amount of heat as compared to object B. Now see, similarly, electrical conductivity. Okay, similarly for electric conductivity also, as we are considering this is wire, okay, or this is any conductor, okay, and we are passing from this conductor I amount of current. Then obviously if this is conductor and current I is passing through that conductor, there is always some resistance also. Okay. If this is object A or if this is conductor A, and this is also conductor B and passing the current I, there also some resistance is there. Depending on that resistance, how much that conductor conducts current or give the conductivity means how much current is conducted by that conductor. Okay, then that is nothing but our electrical conductivity. Now see here, for the thermal conductivity there are three cases. Okay, now see here, how actually thermal conduction is happening. See, first, if I consider this is wire, okay, and I amount of current is passing through that wire, okay, and if R is the resistance of this wire, okay, why actually I am considering here R? because in that pyramid case, after some time I am going to use Wheatstone bridge. Okay, and Wheatstone bridge, actually in that Wheatstone bridge we are applying that resistance, bridge resistance actually, and that resistance is nothing but the wire, okay, or tungsten filaments. That's why here I am considering this wire through which current I is passing. Okay, now if this wire is placed in atmosphere, okay, then what happens? There is a, obviously in that atmosphere when we place that wire, due to of that atmospheric airs or some molecules is there, what happen? As you know, when current is passing through that wire, okay, then due to of that current and depending on that resistance value, that wire is going to hit, okay, means that wire dissipate heat to this surrounding. Okay, and this heat nothing but the Q is equal to I square RT, where I is current, R is resistance, and T is time. Okay, means what amount of heat dissipated to the atmosphere is depends on this I square RT formula. Okay, now second case is that similar, but now we are placing this wire in the high pressure region. Here normal at the atmospheric pressure. Okay, now high pressure region, or we can say high density region. Okay, or high conductivity region. See here now, how high conductivity. Now, if this wire is placed in this high pressure region, high density region, high conductivity region, as high pressure is there, obviously high number of molecules is there. As we studied in our first lecture or second module, vacuum techniques, in that we studied when we are dropping the pressure, means when we are creating the vacuum, there is a number of gas molecules is continuously decreasing. Means when there is a high pressure, then obviously number of molecules in that region should be high. Okay, clear? Now, when that current is passing through that wire, means that wire is dissipating heat. Okay, this is clear. Now, if there is a high number of molecules in that surrounding of that wire, then what happens? That gas molecules collide with this wire, okay, and take out the heat from this to this atmosphere. Getting? Okay, and due to that what happens? This wire is getting cold or temperature is reduced. Understand what happens when there is a high pressure region is there? Obviously there is a high number of molecules or particles is there in that region, and due to that what happens? As we know, wire current is passing through that wire, then that wire should go into heat and there is a heat dissipation in that surrounding. But as there is a number of gas molecules is there, that gas molecules will collide with that wire and take out heat from that wire due to the temperature of that wire is getting reduced. And we can say that resistance is also decreased. Clear? Now see here third point. Okay, third point is for low pressure region. Or low conductivity. Okay, see here, as low pressure region is there and this is wire for which current I is passing through that wire, then As we know, this wire is going to hit due to that equation, and as low pressure is surrounding around that wire, then what happens due to of that low pressure means there is a low number of particles are present in that atmosphere, and due to of there is a temperature reducing is very slow, or conductivity of that heat to that atmosphere is very low as compared to this one. Understand, students? Now see here, if there is a low pressure region, there is a number of molecules are smaller as compared to this one, and due to there is a low conductivity of low thermal conductivity. Clear? Now see here, this is the three basic points for the thermal conductivity. Now see, to go into the periodic gauge, first we are going to study the Wheatstone bridge. See here, Wheatstone bridge. Wheatstone bridge. Now what is actually Wheatstone bridge? See here, Wheatstone bridge is nothing but okay. Now see here, if this is Wheatstone bridge and we are providing a power supply from this, and this is adjustable resistor. If this is A, B, C and D. Okay, A, B, C, D. Now see here what happened actually. When there is Wheatstone bridge is working and we are giving the power supply to this Wheatstone bridge, then as we are providing the power supply to this Wheatstone bridge, then first of all, there is galvanometer shows some current I. Okay, due to of that bridge. Now we have to first null condition is that for Wheatstone bridge is that when that current I null first to the working of that Wheatstone bridge, we have to should when we are giving the power supply to that Wheatstone bridge, then first for the null condition we have to adjust I is equal to 0 for this galvanometer. Okay, and for doing this I is equal to 0 for this galvanometer, we should adjust this resistor. Okay, this is adjustable resistor. Means when there is a null condition, at that point A by B is equal to C by D. Always. Means this there is a balancing of that resistors ratio. Understand? Okay. Now see here. Okay, that is our Wheatstone bridge. Now, periodic gauge is also works with the similar principle of that Wheatstone bridge. Means what is actually happening? See here. See here, student. Now, this is circuit diagram for the Pirani gauge. Now see here, this is to the vacuum chamber. Okay, and this is same be our adjustment resistance C, and D is also resistance. Now see here, Pirani gauge also works on Pirani gauge is always working on the Wheatstone bridge principle. Now see here how. First of all, this is a filament of tungsten filaments, okay, or platinum filaments, okay. Now, as you saw here, when we are doing the power supply, there is a galvanometer show some value of current, okay. And what we are doing by using that adjustable resistors, we maintain that current I is equal to 0. Means we are nullifying that, or we are balancing that bridge. Now see here, what happened? Initially when we are giving the power supply, okay, and this resistance is also connected to the vacuum chamber. Now what happened? As this is connected to vacuum chamber, okay, and this is our power supply. When we are giving the power supply, there is a galvanometer shows some value of current, okay, and we are using that null equation where by using adjustable resistor we are maintaining the current I is equal to 0 on the galvanometer, okay. Now what is actually happening here, when vacuum chamber is connected to this resistance, then or that wire, then what happens, if as due to that power supply this resistance is going to hit and this resistance dissipate the heat around this, okay. Now depending on that vacuum or depending on that material which is around that wire, if that is, as I explained 3 cases, if this is in the atmosphere, there is only dissipation of it. When there is a high pressure atmosphere around that, then there is a resistance is for the high pressure, resistance will low, because as high pressure is there, number of gas molecules is larger, and then number of gas molecules collides with this wire and take out the heat from that wire and go into again the chamber, okay. Similarly, when low pressure is there, then resistance will increase, because as low pressure is there, number of molecules are lower, and that's why the number of molecules colliding with that wire is also low. That's why the heating or temperature of that wire is not reducing, it's continuously heating, okay. But in that case, the temperature is continuously decreasing. Means there is also resistance as decreasing or either increasing. Means we have to again nullify or we are again balancing that bridge by using that adjustable resistors. And by using that adjustable resistance, we are maintaining current value I is equal to 0 on the galvanometer. Okay students, okay. Now see here, as the advantage of that is, this is not much more expensive, okay. We can easily create, okay, we can easily make that Wheatstone bridge, okay. Now second application is that even though that vacuum chamber is much more distance or another room, then also we can use this Wheatstone bridge for measuring the pressure value, okay, because just we have to connect these two in that another room also, okay, and we can easily calculate, okay, and not much more expensive, easily we can create. But disadvantage is that we should have to provide electricity continuously to that Wheatstone bridge, then and then only that will work, okay. Means you have to continuously provide power supply to that gauge, and then only we can measure the accurate value of pressure. And advantage is also you can more accurate value it can give, because what happens, direct as there is a change adjust this resistance and we can find the value. Okay. Similarly, A by B is equal to C by D, and from this we are finding the resistance of here. Because B we can adjust and we know the value of B. C and B is already known. From that we can find the value of A easily. Okay. As we know the resistance value, then for that resistance value we have the corresponding pressure value. Corresponding pressure value. But only disadvantage is another also. For the every gas, if there is a nitrogen, anyone, for the every gas we have to make there is a more calibration for resistance corresponding pressure. How much resistance we have found, corresponding pressure which means we have to continuously calibrate all that. Okay, this is disadvantage.